All right, welcome to the Environmental Water Network webinar. I see a lot of familiar faces, but to those who are just joining for the first time, my name's Nicole. I'm the Healthy Rivers Project Associate with the Nature Conservancy, and I manage the Environmental Water Network. And the Water Network was established in 2019, and it's a collaboration with the Salmon and Steelhead Coalition, which is a partnership with the Nature Conservancy, Trout Unlimited, and Cal Trout. And the goal of the network is to remove barriers to implementing environmental flow projects while accelerating the pace and scale of implementation. And the network really serves as a resource and tool for members to connect, receive guidance, and share resources and technical expertise. Today, I'm thrilled to introduce Bronwen Stanford. She's the lead scientist for the Nature Conservancy, and she's going to share an update on the functional flows calculator, which is a tool that quantifies the 5 core functional flow components of the California Environmental Framework. So with that, I'm going to stop sharing my screen and hand it over to Bronwen.
Great. Thanks so much, Nicole, and thanks to all of you for being here today. Excited to share with you this new and very updated tool that we've been working on. So I'm the lead river scientist here in the Nature Conservancy California's water program, and I'm also the acting director of freshwater science and a member of the CEFF technical team, and I've been working with that group for about the past 7 years. This is a project that was funded by the Wildlife Conservation Board, and the Nature Conservancy has been leading this update, working closely with the team at Foundry Spatial, who have been leading the tool, sort of the technical tool development here. And this whole project is a sort of a product of the California Environmental Flows Framework technical team. And you can see that those are the logos kind of showing at the bottom left side of your screen. So as Nicole mentioned, this update, this tool, which I'm going to get into a bit more what it is for those who might be new to it, it's part of the California Environmental Flows Framework. And the California Environmental Flows Framework, or CEFF, is sort of a structured process that provides technical guidance for managers to help them develop scientifically defensible environmental flow recommendations. It was co-developed by the agencies of the California Environmental Flows Working Group, of which I'm a member. There's the logos again. And it's being implemented in a bunch of different projects across the state. This has been an exciting time because folks are actually getting to start trying to incorporate it into their projects. And I think we're learning a lot from that process, and I'm really excited to see it out in the world. You can read more about the California Environmental Flows Framework at our website, ceff.ucdavis.edu. We have a report and a bunch of resources and papers and fact sheets and lots of information there, other webinars. And to provide sort of a very, very high level overview of the California Environmental Flows Framework, as I mentioned before, it's a structured process, and we've split it into these 3 sections. The first section is section A, or the Natural Flows Foundation, which asks the question, what are the natural ranges of flow in a river in the absence of human activity? And you can use this to sort of think about these quantifiable metrics, focus on functional flows that help you identify ecological flow criteria for your river based on some of those natural ranges. The second section, or section B, non-flow considerations, asks you to think about how non-flow changes to your system might have altered the relationships between flow and function that we're trying to achieve, so that some of those functions might not be performed by the flows that they used to be, that used to perform the functions. Things like water quality, temperature concerns, changes to physical habitat, invasive species, things that might alter the way the system functions. And then you use that information, again, following the structured process, to develop revised ecological flow criteria that incorporate those considerations. And then the final section, section C, is where you think about all of the other goals you might have for your river system, whether it's human water use or recreation or ability to discharge wastewater or water supply, like flood control. All of these other concerns kind of fall into this final section, and then you kind of think about how those might work together or not with your ecological flow criteria so that you can develop um, balanced environmental flow recommendations in this section C. Um, so that's a very high-level overview of CEFF. And something that really undergirds the whole process is this idea of functional flows. So functional flows are these hydrograph components that sort of have an outsized influence on the condition of your river or stream. These are components of the annual hydrograph that support disturbance or promote physical dynamics that are important for the system. They tend to be driving ecosystem functions and are a lot of what lets our rivers and streams support the high biodiversity that they do. And the exact pattern of these functional flows and the types of flows that you would expect in a system is going to vary a lot depending on the type of river or stream you're in. Is it large or small? Is it snow-fed or groundwater dependent? Is it in the really wet part of the state or a really dry part of the state? So that the timing and magnitude of these different flows is going to vary a lot, and this ecosystems that and the species that they support will vary as well. But we found really consistently across rivers and streams that having this, there's sort of a characteristic timing and magnitude and duration of flows that helps that river be itself and that sort of maintain function over time. So these are what we're calling functional flows. And within the California Environmental Flows Framework, we've identified 5 functional flows that sort of capture these annual patterns of variation that are important for our rivers here. So these are the fall pulse flow, this first sort of wet season initiation, flushing flow, the elevated wet season base flow, including interspersed wet season peak flows or flood flows. That'll be more of your channel forming flows. And then a gradual spring recession flow down to a lower dry season base flow. And again, the shape, the exact pattern is going to look different in different rivers, but these general components tend to be really consistent. And as part of CEFF, we also quantified each of these 5 components. So we developed a series of metrics that describe each of these 5 components, things like magnitude, timing, duration, frequency, rate of change, so that we can put a series of numbers to each of these components to describe it quantitatively. And this is where the functional flows calculator comes in. So the functional flows calculator, the tool that quantifies each of the functional flow metrics for each year, for each input time series, so that you can have numbers to attach to your functional flow components for your site in any given year. It uses daily flows to make these calculations, and having these sort of consistently quantified metrics following this really standard process is sort of at the heart of what makes of what supports the CEFF overall as this like structured, consistent process. So having the functional flows calculator and these calculated metrics enables the development of a quick summary of patterns in stream flow over time. You can compare what's going on in your system to historical or predicted future conditions, or you can compare it to what you think should be in the system in an unimpaired condition. You can do assessments of alteration by comparing what you see or what you might see in the future to what you think would be there naturally. And then if you use unimpaired flow data in the functional flows calculator, you can sort of quantify what a potential ecological flow regime based on functional flows might look like in that system. And we've had a functional flows calculator for since like 2018, 19, I think it was finalized in 2020. But this is the first major update we've done. And it builds on the work from the first calculator and a bunch of other work that's gone on in the past 5 years. So it integrates our statewide hydrologic classification, describing some of the variety of stream types across the state, which it uses to sort of adjust the calculator for different parts of the state and hydrologic conditions. It builds heavily on the original functional flows calculator and web tool. We preserved that calculator intact as we moved it forward. There's been an R package that I think a lot of folks have used. I know I've used it a lot to access the original calculator. We integrated a lot of those functions. And then we have predicted functional flow metrics. We have an alteration assessment. We have new dry season metrics. And then we actually have a whole new calculator that works really well in flashier, really altered systems, and I'll talk about that a little bit more as well. So it's able to bring a lot of the work that we've done together into one package. So I'm gonna step through some of the calculator in a minute, but just one more sort of overview slide. So major upgrades or updates to this version, it now has a searchable map with all USGS and CDEC gauges that you can scroll around on or search or select. And it includes metadata for all of those gauges, including whether or not we're considering it a reference gauge or sort of a least altered gauge. And that's the set of gauges that we use to predict unimpaired conditions, which I'll get into a little bit more later. The years of record that the gauge was operational, the hydrologic stream class we associate it with, and the COM ID. We also have developed some new visualizations for the results and also for assessing alteration. And then, as I mentioned on the previous slide, it incorporates a lot of the recent work that the technical team have done, including these additional dry season metrics, this alternate calculator, alteration assessment with box plots, and then the R package functions. Okay, so then to walk through the tool itself a little bit, after you enter the tool, this is the page you see. This is our searchable panable map with all of the USGS and CDEC gauges on it, visualized with these different symbols. You can choose whether to see all the gauges, turn off gauges entirely, or just look at the reference subset of gauges. So these, again, are least impaired gauges if you want to get a sense for what those would look like, or if there's a reference gauge near your location of interest. We have all each stream reach is color-coded by one of these, it's 9 stream classes. And then once you click on an individual gauge, more information comes up, including the gauge ID, the gauge name, and the date range over which the gauge was active. And then you can choose what subset of years to run through the tool. You can use the entire date length, or you can specify some subset of years that is important to you. I don't have a box to highlight it, but up here at the top of the map, you can also search by a bunch of different things, including COM ID, gauge name, gauge ID, stream name, place name, I believe. So that provides that can be really helpful for getting to your gauge as well. And then if you don't want to use one of these gauges or your gauge isn't here, you have your own data set, you can also upload your own file of daily flow values to run through the calculator instead, and then just choose the appropriate COM ID for your location. And then the next thing you have to do is you have to choose a calculator type. In almost all cases, almost all people should use recommended. This will assess your data set and then select the best calculator for you based on characteristics of the data set and the type of stream that it's on. If for some reason you do want to choose, you still can. You can choose reference. So reference is the original calculator that we released originally with the original functional flows calculator. And it works best on most rivers, especially rivers with a seasonal flow pattern and sort of like relatively gradual increases and decreases in flow. We also have developed this new, as part of this grant with WCB, this new flashy calculator, which works best on flashy and ephemeral rivers, or highly altered rivers, which have really dramatic changes in flow that are sort of more angular hydrographs. And these are systems where when you ran them through the reference calculator, it wouldn't calculate in a bunch of years, and it was really hard to draw conclusions. So if you choose recommended, hopefully most of you will choose recommended, the tool will assess for you which of these two calculators is going to give you results for the most years and which one's probably most appropriate for your data. Okay, and then you are brought to this. Oh, go Nicole.
Oh, there was just Jesse had a question in the last slide about what are the
Yes.
different stream classes in the map legend.
Yeah, they don't show up here, but if you click on one, it does like actually define what they are in words. Over on can you even see my cursor? I think you can't. but
We
over,
we can
you
see
can,
it.
okay. Yeah, so it will put it into words over here, but the classes are like snowmelt, high volume snowmelt and rain, low volume snowmelt and rain, winter storms, groundwater, perennial groundwater, I think, flashy ephemeral, rain and groundwater, HLP. I don't even remember that one. That's not a very common one. Um, but yes, yeah. So there's sort of these 9 hydrologic classes. And there's like links in the tool to a paper describing them and more information about that data set too, if that's helpful.
Awesome. Thanks, Bronwen. Monty also had a question. Would a small coastal bedrock dominated stream be an example of flashy?
Um, no, I mean, it depends where in the state you are. I think in Southern California, probably, because probably it's a case where there is rain, very small amounts of rain for a very small period of time, and then there is no water at all. I think so. When we say flashy ephemeral, we are really talking about like the classification that is used here. So you can go into this tool and look at how your stream is classified that you're interested in, and if it's showing as FER, um, which some small, I mean, depending how small the stream you're envisioning Monty is, it might, I'm not sure, but you can go and look and see how we would classify it. And if things that we're really talking about things that fall into this category. I mean, a lot of streams in California are some degree of flashy, but I think we're talking about more like extreme changes in flow. And the real concern is like the original calculator, a big part of how it works is sort of it applies smoothing to allow the calculator to pick out patterns, like where is the wet part of the year, where is the dry part of the year. And if you smooth like a right angle, you end up with a result that doesn't really make sense. So yeah, I hope that helps, but happy to talk more about it. And basically, I think we found that in cases where the reference calculator is able to calculate good result, like consistently calculate results, it often performs better because the smoothing can be sort of more like the approach that it's taking, I think works better where it works. But we found that for these really dramatically um, abruptly, this is really abrupt flow changes. It wasn't even able to detect the changes and find the changes in seasons consistently, and it wasn't calculating at all. So in those cases, the flashy one is a better choice. Um, and we have this is one thing. So we have there's a report going into more detail about like how this calculator was developed and sort of comparing use cases that we are about to post. It's going to be, it should be live by the end of the month. But that's a link that will be updated within this website. So you'll be able to go there and get more information about it. Any more questions? Okay. Okay, so into a brief overview of results. So you are brought to this results screen. Um, and this is sort of modeled on the original calculator for those of you who used that. But you can toggle on and off timing metrics and magnitude metrics, either overall or by functional flow component. We've also incorporated something that's new on this tool, the natural or predicted natural ranges by water year type for each component. So you can turn those on and you'll see this series of sort of shaded boxes that indicate that the timing and magnitude in 50 and 80% of years that you would expect to see that flow happening naturally. So you can compare that to what you're seeing in a given year. So in this year, the spring recession timing is sort of at the edge of the 50th, the like 75th percentile, and the timing and the magnitude for spring timing is sort of at the top of this box. So it's sort of like what you would expect to see in sort of the wetter, the sort of the 90th percentile wetter type of year. So yeah, so in this tool, like each component has a vertical line to show magnitude that is color coded, and then a horizontal line showing the duration. Sorry, I said that wrong. Vertical line showing timing, and then a horizontal line that shows the magnitude and duration of that component. And if you get in there and can click things on and off, I think that will probably seem clearer. There's also a slider bar, scroll bar at the bottom, so you can move through year by year to look at data in different years and see how the metrics change. You can download data, a whole series of CSVs, which I'll show in a moment. And this is a scroll bar, like there's a lot more metrics down here that you could get to as well. So if you download data, there's a whole package that you get. You get the results of an alteration analysis comparing your data to our predicted and impaired data set. You get box plots doing that same comparison. There's metadata on the data that you ran through the calculator and sort of the parameters it used, the COM ID that it used, the calculator it selected. There is a CSV of daily flow data organized by water year day that was used to run the analysis. This is sort of the big result, the calculated annual functional flow metrics for your data set. Then there are percentiles on these results that are sort of calculated if you want to see a more like process, like statistical, like what are the statistical distribution, I guess, of your data instead of looking year by year. And then any warnings, including information on years that were skipped. And there's more information about all of this on the website as well. And I've mentioned them a few times, so I thought I would provide a little bit more information. So one thing we're referring to, especially for the alteration assessment, is these modeled natural functional flows. So this was an earlier part of the project. I think this was completed in 2022. It was led by Ted Grantham and others within the CEFF technical team. And we predicted natural functional flow metric ranges at every stream in the state. So using that set of reference or least impaired gauges, we trained a model, and then we predicted the ranges of natural functional flows for each metric all across the state. And then we used a combination of model predictions and reference gauge data, depending on model performance and sort of the amount of natural variability that we were seeing for each of these metrics. And most metrics are reported by water year type. So you'll be able to look at the alteration assessment both overall and then by water year type. What are we seeing for alteration, and what do we think that the natural ranges are likely to be? And again, just briefly, for those of you that aren't familiar with it, those predictions, which are pulled into this tool for some of the visualizations, are all available on our companion site, rivers.codefornature.org. It's also linked to the functional flows calculator, where you can see the predictions for each functional flow component and metric for all of the reaches in the state. So the alteration assessment is sort of the next visualization I wanted to talk about, or next component of this tool. So this compares the computed functional flow metric ranges to the predicted natural ranges by water year type and overall. So it does that comparison to say, like, if we look at what you input or the gauge that you chose to run and compare it to the predicted ranges, like how different are they? What's the distribution of those values? And it's one thing that's important to know about this, it's sort of a coarse screening tool for alteration. It is not going to catch everything. It may give you an unaltered result and there's still some alteration, but it's sort of a broad first pass to see, like, is this likely to be a very altered system or not? So it's coarse for a few reasons. One is it looks over the entire time period of the input time series, potentially by water year type, but over the whole period. So you can't, if there are trends in your alteration, like it's been increasing over time, but it was pretty unaltered towards the beginning of the time period that you uploaded, that might swamp it out. So you won't see the alteration maybe that you're seeing in the more recent time period. It does this comparison either for the whole package of data overall, comparing what you see to like what we expect to see, or by water year type, but it doesn't do like a year-to-year comparison. So if you're in a river that has a lot of variation year to year, some of that alteration might get a little swamped by just the natural variation in flow that you're seeing. And then there are also cases where our model for the predicted natural ranges has a lot of uncertainty or really wide predicted ranges. And in that case, again, it's going to take a lot of alteration to bump you out of the natural range. So you could have a system that's pretty altered, and because the model isn't sure, because the natural alteration is so high, or both, it could be hard to show that you're actually seeing a different distribution of data because of alteration. But it can detect like big patterns of alteration and be a flag for further exploration. So we in this version, we incorporated the alteration assessment, which had been part of the R package for those people who'd been using that. And we created a visualization to sort of help people navigate that data. So here is this schematic, so generalized, it's the same for any river you pick of the 5 functional flows. The thing that changes is the colors of these blobs, which show the likely level of alteration. So if you have very little data, you can't do an alteration assessment. If you have 5 to 14 years of data, we're saying you can do a possible alteration assessment. And then if you have 15 or more years of data, we're saying it's likely. You can do a likely alteration assessment. So this fall pulse didn't occur in a lot of years. So there's between 5 and 14 years of data. So this is shown up as possibly unaltered. And then we have a couple of likely unaltered and likely altered. If you click on one of these components, so this case I clicked on spring recession flow, you can see more information where it shows each of the metrics that fall under the spring recession and whether they're showing as altered or unaltered. So in this case, 3 of them were not altered, were likely unaltered, and 1 of them was likely altered. But because you have to look at the component as a whole, if anything is altered, you should look in more detail, is sort of our philosophy, because these are interrelated. So the whole component is considered likely altered. And then we also created this graphic. So if you click again on this likely altered spring recession magnitude, here's a plot that shows each dot is a different year of data in your input data set. The blue is things that sort of are above the 90th percentile of what was predicted. So you would only expect like 1 in 10 years to be up here. The red is below the 10th percentile, so you would only expect 1 in 10 years to be in the red. And then the white is where we'd expect most values to be. So in this case, it's likely altered low because a lot of these dots are down in the red as opposed to blue, white, and red, and mostly in the white. So that's that. This is, I know, a lot of information. So we also have developed a pretty detailed science and methodology page as part of this tool that walks through the sources we use to build it, some of the methods, definitions of the metrics, some details sort of walking through what the different visualizations and results mean, and references. We also have a frequently asked questions page that we hope to keep updating for things that common questions people might have. So I'm hoping as more people use this, you'll send us questions and we can keep building that out. Just a couple more things to mention, and then we can open it up if people have any more questions. We also have an API. So if you want to be able to access the calculator directly from within some coding language, we included code snippets for both R and Python that will walk you through the steps to get it running and upload your time series or select your gauge ID and then return results that are really similar to the downloads, the same as the downloads I walked us through earlier. So yeah, if you don't want to go through the graphical user interface piece in the map, but you just want to pull the data directly. And then we also, as part of this, I'm not going into this in a lot of detail today, but initially there had been this separate Python code base, which is sort of the engine that drives the online tool. And as part of this process, we also sort of updated the Python code base, integrated the new flashy calculator, some new dry season metrics, which I didn't even get to today, but we have a few new dry season metrics, and incorporated some more functionality. So this Python code, which is available easily downloadable on GitHub, supports batch processing. If you want to run a lot of gauges at once, it has some instructions for how to do that. So you can just like upload a single CSV into the tool and it will run hundreds or however many you want. And it has all the functionality of the web platform except for the visualization. So you can choose to do the alteration assessment and look by water type and calculate percentiles, etc. And it runs locally on your machine using the downloaded code. I mean, you can also use this if you are more interested in getting into the details. You can use it to look at what the calculator is actually doing, explore the code base on your own. There's a bunch of annotations to help describe things. And if there's some specific need, you can also modify some of the parameters that the tool is using on your local machine. We've set this up so that you don't need a GitHub account and you don't actually need any Python experience. I'm very bad at Python and I have successfully run this many times. So that should be pretty user friendly if you are someone who wants to run a bunch of data. So that's what I had. I can do a live demo, but if there are any questions, I'm also happy to take those. And for those who don't have it, which it's probably did someone already put the thing in the chat?
I
Yeah,
just put the GitHub and some of the other links that you mentioned in the chat earlier.
Okay, great. Okay, cool.
Yeah.
I just put it again. But
Oh, great. Looks like Michael, you have a question. Do you want to go off mute and ask? I can also read your question if you'd like.
Oh, sure. I guess you can hear me?
Yeah, we can hear you.
All right. Well, so I'm interested in how the statewide results. You mentioned that you used the flow calculator to functional flow calculator to go across the entire state with all the functional flows, maybe with unimpaired and impaired flows. I'm not sure exactly, but is this information being used to inform the water board's decision making on the Bay Delta and the ocean plans? And if so, how, or if not, why not?
So your question is whether the functional flows calculator is being used in the Bay Delta plan update? Water
Right.
quality? No, I don't think it is at all. So there's a few, I mean, yeah, why not? So
No,
I
it's
guess
okay. It's a big
so.
question, so you don't
No,
have to
it's
answer
a
it.
reasonable question because I know that's probably on the top of many people's minds at the moment. So we, yeah, when we developed our predicted functional flow metrics, we explicitly cut the delta, not the whole of the like Sacramento, but the delta itself out of those predictions, partly because the natural habitat and sort of the way that water moves through the system is so extremely altered in that part of our state that sort of the natural relationships between flow and function are just very different from what they would have been historically. So understanding natural flows there is, I think, really important. And also like to understand how to develop functional flows, the process in the system that's severely altered is just going to be more complicated. And that's a place of the state where we have so much modeling and so much information and so many people working really hard. So I think honestly, we have developed a lot of these tools to work maybe in the rest of the state that isn't getting as much attention as the Bay Delta is. I think it was developed and I think does work really well below major dams where we're trying to think about what a more natural flow regime would look like. And we've done some work on some of the tributaries to the San Joaquin. We're doing some work actually kind of across the state on some of the major tributaries to the Central Valley, exploring functional flows and how those what those might look like, how much water they would take through the Co-Equal project, which maybe some folks on this call have heard of. But yeah, and maybe to answer the first part of your question, so the functional flows calculator can work on unimpaired data, it can work on impaired data, it can work on any sort of daily flow time series you give it. and it's going to just quantify those functional flows as best it can find them within your annual like flow time series. And
Okay, well,
yeah.
it's kind of a two-part question, so thanks for that answer. The second part that goes with that is that when you look at the system as a whole with regards to fisheries, really you have to look at the functional flows in all throughout the whole system. And of course, we all know that the ocean itself, the bay itself, and the delta itself is embedded in that functional flows that we use in order to do a mountain stream. So if we're in a mountain stream and we're looking at the functional flows to increase fisheries, part of that embedded function for the fishery is how the delta and the ocean and the bay responds to our stewarding of that mountain stream. So that concept of functional flows, and I like the calculator, but it seems as if you have to really carry that functional decision making and that modeling all the way down through the whole system in order to see where the links are broken. And I'm wondering how we could, what would you suggest, how we could show using the functional flow calculator, how we could show the water board how that should be done in order to help them make decisions as our trustee for the allocation of water and for the protection of water quality.
And are you again thinking specifically of like Bay Delta stuff? Or are you thinking just more generally, just the challenge of managing our complicated watersheds?
Well, if you go from the top to the divide all the way down to the ocean and you can do a functional flow at a particular station, then you did that as you went through. And right now we're saying, well, it's too difficult to go through the delta with that because of the impairments that have occurred. Well, we can actually show that, well, the impairments are actually occurring a lot higher than that up in the river system. Let's say where the Sacramento has been straightened out or levied, or the Yuba has been straightened out and levied. And so you can actually see through these functional flows that you just described, all those characteristics, you can actually see then, well, this is the next thing downstream from us that is an issue. Noting that, of course, the big issue is the Bay Delta. So that's what I'm thinking when I listened to your presentation, which was very good. Thank you. So
Yeah, no, for sure. I mean, I totally agree. I think being able to look across the whole system and sort of manage the whole watershed is definitely what's going to be what important and what's going to actually bring us back to functional systems. Addressing like one small reach or tributary, especially if we're thinking about species that need to move up and down our rivers, like salmon or steelhead. Like thinking about that connectivity and condition along the whole river for sure is going to be really important. And we are doing a project where we're using the functional flows calculator, and we are like developing like a functional flow regimes for the major tributaries to the Sacramento and San Joaquin valleys, and kind of trying to follow that flow all the way downstream and think about like how much water would this be, and how different is that from baseline, and where are places where we're really, really not providing these flows right now, and like what would impacts on other uses be of providing these functional flows, and trying to understand like if we just look from a water perspective, like what do we think the gap is, and where are spaces where we can think about trade-offs and management options. So yeah, I totally agree. I mean, one of the goals of this is trying to make it easier to at least have some sense for what ecological flow needs might be, so that it's more possible to think across broader scales, across watersheds, about where impairment is happening and how to adjust management. So yeah, thanks for that question.
all right, thanks. I didn't want to take that much time up. Okay.
One thing I might, people can ask more questions, but one thing I might just show briefly is so this was a lot. So if you go to the functional flows calculator page, we have this science page, which has a lot of links in it. And this key resources page at the end, especially has like links out to the functional flows. Sorry, this is really small. Links out to like our CEFF webpage, information on metric names, information specifically more on the calculator updates. We're going to add the flashy calculator documentation in the next week or so. The Python repository on GitHub, the natural predictions definition. So it has a lot of like, this page is long. I apologize for that, but it does have a lot of sort of links out and information on what we've done, why, and how to understand more about the tool. So hopefully that will be useful to folks. Yeah, I don't know. Are there any other questions?
Yeah, I can come off mute here. This is Daniel Mountjoy with Sustainable Conservation. I just put a chat in the message there around how do you envision using the tool to explore and examine future projected climate change hydrographs. I'm just wondering how the tool functions in terms of identifying what's the natural functional flow, and if you throw in a projected climate change hydrograph, what does it do to the natural? It's still comparing it to the historic natural function. I guess if you could talk a little bit about that, I'd like to know how to interpret.
Yeah. Oh, I think maybe you froze. I think I got most of Daniel's question now. So yeah, I think that's a great question. So the calculator itself, I think, could work really like the calculator itself just sort of takes in whatever daily time series you give it, and it will calculate these metrics in a really standardized way. So if you feed it data for some climate future, it's going to take that and be able to describe back to you like what will functional flows look like in the future for your river? Like, are we going to see like what's sort of the range of timings we would expect to see for the spring recession potentially? Or are we seeing a later, like what's the timing for the beginning of the wet season, or what the magnitudes look like? The way that we have it set up, right, like the sort of the default way that it does its alteration assessment and the comparison that it will do automatically for you is, as you said, yeah, comparing to our historical time data set, which is from 1950. It trained on data from 1950 to 2015. So the default way that it will work is it will compare whatever you put in to the ranges we would expect to see in that 1950 to 2015 time period. However, you can also like put in whatever like sort of comparative. You can also use the outputs and compare them to functional flows calculated on any other data set that you think is a better representation of your system under current alterations without climate change, or your system under climate change with no alterations, or some baseline condition, to do those comparisons and see like try to isolate the effect of climate. And I think it kind of depends on the question and what you think is most important to understand about your system. But this tool can support any of those uses.
Yeah. Thanks, Bronwen.
Yeah, it's a good question.
There's a question in the chat if there's time to do a short live demo.
Yes, that sounds great. Does anyone have a selected location, or should I just pick randomly? This is the search bar, where you can put in different locations, and then you can also
Pescadero Creek was
okay,
offered in the chat.
great. Don't not find it for me. Did I spell Pescadero wrong? No, I did spell Pescadero wrong. Sorry, folks. So it zooms me into a part of Pescadero. Does that see in Pescadero Creek? Yeah, no, I'm assuming you mean this one. Probably. I think that's a different one. So we have one gauge here. So yeah, so it highlights the stream in this sort of bright teal color, and we can click on the one gauge, which is showing up in purple here, which is a USGS gauge. It has data from 1951 to 2025. It might be, I don't know if it has every year in that period or not. And it's a reference gauge, so we can choose to use the reference period, which ended in 2014, or we can use the whole date record. I'll use the whole date record. And we could also choose to specify some different subset of years. Next, I'm going to use the recommended calculator. Calculate. This is going to be faster soon. It's a little bit slow right now because it's generating box plots. But we're going to make that optional in the next update to be released next week. So this will get a little faster. Or I think it's about 4 times faster when it doesn't have to do box plots. And then, yeah, it'll bring us to our 2 results pages. That was a gauge with a very long record, which is fun. I'm sorry, this is very slow. And as a warning, the USGS gauges will be much faster than this next week, but the CDEC gauges are still very slow. We've found that API to just have a very slow response time. So we're like pulling data from CDEC and it takes a while. So as of next week, this will not be slow, but the CDEC ones will be. I'm gonna just make this a little bit smaller because my screen is. Okay, so then we end on our results page. And we can see that there's this really long period of record. The first year only has a partial water year, so there probably aren't going to be any metrics calculated. And we can turn on our timing and magnitude metrics, all of them. And then if we move forward to a different year, maybe all is too much. So we can turn on like spring recession. Does this look okay on your screens? You can see okay? It's not too slow.
Yeah, it looks good on mine.
So we can click on the spring recession start timing, the spring recession the spring start magnitude. We can see it sort of identified this as the spring recession. We can turn on the natural predicted ranges for the spring recession. So it's kind of on the edge of what we'd expect. If you sort of hover, this will follow the hydrograph along and show you the values when you get to, I'm not getting it, but when do you get to one of the flow components? And we can do the same for the others. So there's like the dry season start timing, the dry season low flow timing, dry season base flow values, which are really hard to see because they're so low. We also have an option where you can turn it onto log scale if you want to, if you're more interested in looking at the dry season. Add the fall pulse, and sort of ranges for the fall pulse, which are also kind of have to be on log scale to see properly. And then peak flows, which are the same values in every year. And you can see whether, you basically have to look and see whether or not your line crosses them. So this is a really helpful, I think one of the reasons I really like this visualization is it lets you understand what the calculator is doing. Like it's easy to get the table of values, but this lets you see like, the thing it's calling a fall pulse, like, do I agree that was a fall pulse? Does that look right? Oh yeah, that actually does. In this case, looks pretty good to me as a fall pulse. And like, this is the timing is choosing for the spring, for the dry season. Like, does that seem reasonable? I didn't turn on the wet season, but you can also see like the timing and magnitude it's choosing for the wet season. And maybe that wet season looks a little bit early, but it seems generally reasonable. So yeah, and then you can, if you click through to different years, it'll keep adjusting the plot and the location of the metrics because the metrics are calculated for that year. And it also tells you up here what year it is and water year it is, and then also the water year type. So this is this is a dry year. That looks like a very dry year. And then a moderate year and a wet year, and sort of how the hydrographs and also the metrics vary. And you can also choose to fix the y-axis so it looks the same in every plot to let you compare more easily.
Anne asks in the chat if you can display lots of years overlaid on maybe a new line each 5-year increment.
You cannot do that, unfortunately. No. So the only option here is to show it year by year. But good question.
So Michael also had another question. Is there a way to support more gauges, like citizen science groups, financing the installation of gauges, and then having the gauges station maintained by others?
So those aren't incorporated in this tool because there's no easy way for us to like pull that data off of the internet to analyze it. But those data can totally be great. So the only thing to look for is you still need to have data for the whole water year. I think we allow up to 36 days of data to be missing. So a lot of more like citizen-led or like smaller organization temporary gauges might only have data for part of the year, like just for the dry season. You can't run that in this calculator, but if you have a full water year of data, you can use the upload daily data option. Super easy. Just there's like an example of how to format your CSV, upload it, and it will run it just the same. So yeah, so those data can still be in here, but you just have to upload them yourself. And it's mostly just there was no easy way for us to find and pull all those data in together. We are going to have a process to check for new gauges coming online, USGS and CEDEX, so we hope to be able to keep incorporating and updating that as more gauges are available. And then if we come to this alteration visualization, so for all years, there's a bunch that are indeterminate. And if you hover here, this is way too small for you guys to see, but it includes definitions of what each of these categories mean if you hover. And there's also more information in the like science page. But we can look at all years and we can look by different water year type. There's a lot of indeterminate in this one. So if we click on one of these, it looks like it's probably indeterminate because, and I didn't go into this definition, but it's probably indeterminate because the median observed, this black line, is falling in the white space, like it's kind of where we expect it to be. But there's a lot of dots above and below where we expect them to be. There's a lot of white dots or observed values in the blue and the red. So we're seeing more variability in this location than we would expect to see according to our model. And that could be a few reasons. It could be the model is not doing a great job in this location. Or it could be that there is something about the alteration that is causing there to be more variation in how this how the patterns of flow here. Yeah, like this one is so like the wet season base flows are much higher than the model thinks they should be. We have an FAQ on this. I will say, I think the alteration assessment can be interesting, and I actually really appreciate being able to look to just see the distribution of data for each year and sort of is there a trend or can I see wet years and dry years? Or how is it, what is the shape of the white dots? But we do emphasize this is sort of like a first cut tool and it is not going to reflect everything we know about our rivers. And I think we're hoping to continue revising the rules for the alteration assessment over time. But that's the brief tour. Any other questions? I think we're almost out of time, but if there's one more.
If anyone has a question, feel free to go off mute. I'm not seeing anything in the chat.
I have one more thing. That's really good. I really liked your presentation. This is Michael Ross. And when I was watching you go through the functional flows and showing the graphs for the years and stuff, I would really like to be able to show this to other people in that fashion with the being able to show the steelhead or the salmon and that graph and the amount of flow that's in the stream at that particular point in time, and whether or not that's a functional flow for them to travel up and spawn. And so like that little bubble that was in the graph, if there's a little fish icon that could be used that say, okay, and you could set a functional flow that would show that this is a functional flow for the habitat of the fishery, and this would this type of flow would be indicative of a healthy landscape for them to travel up. And then also this would not be during drought. This would not be a flow that would support the fish, and they would get trapped at a certain location based on the landscape. So that's what I saw when you made your presentation, and it seemed like it'd be very powerful to show people in a presentation that on the local level for their stream.
Yeah, like kind of combining some of these visualizations with more specific information. Like we know that migrating fish need this amount of water here. Like how is that comparing to the functional flows? How is that comparing to the data, the flows we're actually seeing in the system? How does that compare to natural flows, and kind of bringing all those pieces together?
Right. So I think JSON and some programming it might be able to look at a way in which to bring that data into it through the API and look at and maybe with some AI look at the fish going upstream during that graphed presentation. It might be very doable right now.
Yeah, that sounds cool.
Anyway.
Sounds cool.
All right. Well, thank you so much, everyone. Thank you, Bronwen, for that great presentation and overview. We're working on some exciting webinars for the next few